One more to go, and then you're free. And it'll be fun. An XSLT compiler written in XSLT. This paper is jointly with my colleague John Lumley. There's the Saxonica team. John is the guy on the left. Unfortunately, he can't be here because he's holidaying in Namibia. Poor him. And I'm the guy in the center, but you know that. So why would we want to write an XSLT compiler in XSLT? The answer is, if you want to write a compiler that's portable across platforms, the traditional way is to write it in its own language. So you get portability. We're after portability because people want XSLT 3.0 on lots of platforms, and there aren't lots of people out there nowadays writing XSLT processors. So they come to us and they say, can we have your processor on our platform? And the immediate objective is that we've got a runtime version of Saxon in JavaScript, but we don't have a compiler in JavaScript. So first thought was write a compiler in JavaScript, but no, let's write it portably so that we can put it onto other platforms as well. Let's write it in XSLT. And the question addressed in this talk is, can we actually make that perform? To put this in context, John Lumley wrote the compiler. It was about 95% complete in terms of the number of tests it passed. Some people would say that's only 50% complete in terms of functionality, but let's hope it's better than that. And I think 95% functionally complete is a good time to start thinking seriously about performance. And so said, you know, stop before we do the last 5%. Let's just look at whether this thing will actually fly in terms of performance. And so I started a project of studying the performance. So what does the compiler do? This is where it sits in the architecture. Call it the XX compiler for XSLT and XSLT. That's just internal working name. Whereas the XJ compiler is the existing compiler that you all know and love, which is the XSLT compiler written in Java. So they're both functionally equivalent. They take an XSLT style sheet. They produce a style sheet export file, which is really just a serialization of the internal expression tree in either XML or JSON. And then you have a runtime. Currently, we've got two runtimes, a Java runtime, which can be cross-compiled into other languages, but it's basically Java source code, and a JavaScript runtime, which currently runs in the browser, but which we hope to get running on Node.js. And that takes a source document, reads the style sheet export file, either interprets it or does code generation or whatever. So you've got a runtime component here to produce the result tree. Try and make that a little bit more real by showing you a Ceph file. Here's, I haven't got it up there. The screen all looks different now. I've plugged it into HDMI. Yes, here's the Ceph file. This is the compiled version of the XSLT compiler, having compiled itself into a Ceph file. It's about 4 megabytes of junk. And just to give you a feel for the kind of level of abstraction, CO is a component, so that's a template or a function. So the templates and functions and global variables in your original source are still quite visible in the Ceph file. It's added type information, saying this is an attribute, that's an inferred type, rather than something that was on the original. It's inherited a lot of stuff. It's quite confusing to read this because this is the compiler in itself, so the things it talks about are all XSLT sort of construct. It says what module things came from and what line numbers. It's got a line number there. It's got various flags for Boolean operations to decorate the tree. It's added type checking. One of the main things that you do during the compilation process is to add a lot of type checking logic. So it works out whether a runtime type check is needed, and if it is, then it injects a runtime type check into the tree. And this is one of those type checks, and it adds things to actually enable you to produce meaningful diagnostics if the type check fails. So, you know, the usability, it's not just enough to say that the type check failed, you've got to say why it failed and how it could have succeeded. So all that information gets encoded into that tree. And that's basically what the Ceph file looks like. So the UF call is a user function call. That's the function that we're calling. It's called record namespaces. It's got an argument which is dot, which is the context item, and another argument which is the empty sequence coded as empty. So that's what the Ceph file is all about. Oops, that's not what I meant to do. Never use a keyboard standing up. So what do compilers do? This is true of both of the compilers. They have an awful lot in common. There's a lot more detail about the compilers in the paper, including areas in which they're different. But roughly, the first thing they do is static preprocessing. That means dealing with the includes and imports in your XSLT, means dealing with the use-whens. If you've looked at XSLT 3 at all, there's more to be done at preprocessing phase, things called shadow attributes, attributes with an underscore in front, which get expanded at compile time, in fact at preprocessing time, into ordinary attributes. So there's a static preprocessing phase, then there's structural validation and normalization. That means checking that every XSL choose has an XSL otherwise at the end and nowhere else, and that you don't have an XSL otherwise other than as a child of XSL choose, and that Boolean attributes have correct values, and normalizing the values, so once you've gone through there, you don't have to worry about whether it's written as yes or one or true. It's all a single value. There's then XPath parsing. And now XPath parsing is not written in XSLT. That's the one part of the system that's it's still written in either Java or JavaScript. That's basically because we had those parsers already and didn't want to rewrite them in XSLT. But also, I guess we weren't confident that we could get the performance good enough at that kind of level. So that part of the system is still Java or JavaScript. Binding component references, that gets a lot more complicated in XSLT 3 because of the separate compilation of packages idea, which I'm sure I've spoken about at one of these previous conferences. A lot of type checking, I mentioned that, injecting code for runtime checking if it's needed, detecting type errors if you can detect the type error statically. Then optimization. The new compiler does very little in terms of optimization compared with the Java one. That's one of the differences. There's a lot of scope for doing the optimization rewrites as another separate phase at the back end of the compiler, but it's not something we currently do. Streamability analysis for XSLT 3 streaming. We've written a streamability analyzer in XSLT, but we haven't yet integrated it into this compiler. That's another job perhaps for the future, but unless we're going to support streaming on Node.js, which we don't currently plan to do, there's no point. And so that's what the compiler does, and it's much the same for both cases. What's interesting, well, first of all, a compiler operates in a series of phases, and each phase does a tree-to-tree transformation. You look at all the compiler literature, that's how they describe the process of compilation. We've got about 6 phases there, depending exactly how you count. And that's what XSLT transformation is all about. It's about transforming trees into other trees. So if you've got a language for transforming trees into trees, then it ought to be ideal for writing a compiler, oughtn't it? It ought to be the perfect language for the job. It's not, but that's another matter. And one of the purposes of this exercise was to find out why it's not and what needs to change in order to make it better at that job. So differences between the XJ compiler, the compiler written in Java, and the compiler written in XSLT. Well, the main difference is in the data structures inside. Both are using a tree to represent the evolving analysis of the source program. They start with a tree that's very much in the source language vocabulary of XSLT. They move to a tree that's in a more internal vocabulary. The difference is that with the Java compiler, that tree is mutable, and you can decorate it with any arbitrary object values. So you can stick anything onto that tree that you fancy that's a Java object. Now, the fact that it's mutable makes it quite easy to work with. It also makes it very dangerous to work with. We have had an enormous number of bugs over the years through that tree becoming corrupt. Object orientation, in theory, enables you to encapsulate things and ensure that your data structures don't become corrupt. Doesn't work when you've got concurrent access. So we've had multithreading bugs affecting that tree through failure to synchronize. Java does not help you with that process in the slightest. Also, the encapsulation doesn't help you much when you've got integrity constraints that extend beyond an object. It's intrinsic to doing a tree rewrite that you need to change the parent to point to the children, and you need to change the children to point to the parent. And there's actually no way you can encapsulate that operation within one object that says all the updates are sort of atomic and correct, and there's no way of doing a bad update. So we've had a lot of problems over the years with an update to the tree that was abandoned halfway through and left the tree in an inconsistent state, and led to a null pointer exception or something else happening later on. Or subtrees that ended up being linked to by more than one root. And so someone made a change to this branch and didn't realize that someone else was interested in a copy of that subtree. Those sort of issues. So the mutability, if you're working with an immutable tree, then you long for the ability to update it. If you're working with a mutable tree, then you long for the restriction that says, I wish no one could make arbitrary changes to this thing. But then the other point is about the decorations applied to that tree. If we want to decorate that tree with types, for example, then the type information has to be encoded in the form of a string, because XDM restricts you, at least when you're dealing with an XML tree, it restricts you to strings. We've got maps and things now when we couldn't do this without data structures like maps. But you can't attach a map as an attribute value on a tree. It would be really nice if we could, but we can't. So there's a lack of orthogonality in the data model there. And that's perhaps one of my aspirations for the future, is to get rid of that lack of orthogonality and allow you to have, for example, map-valued attributes. I think that would be really nice. So we're not just talking about the compiler, we're talking about its performance. And in any performance exercise, you're following a process. I call it the performance engineering process. And you always start off setting targets, don't you? You've got to know where you're aiming to get to. Otherwise, you'll go around that loop forever and never stop. Next thing is you've got to be able to measure things. Measurement is the key. Making improvements is easy. Measuring them is hard. The tough thing about performance engineering is measurement. It's not speeding things up. It's knowing that you've speeded things up and knowing how much and knowing the effect of your changes. So when you've measured things, you ask whether you're done. If you have done, you stop. Please stop when you're done. Great temptation to say, no, I can improve this still further. If you haven't achieved your targets, you then need to do analysis and say, why not? And there you're doing a different kind of measurement, typically. You're measuring internals. You're working out where the costs are going. You're working out, perhaps you're doing experimental things. If I made a change, what would the effect be? You're doing those sort of processes and then you make an improvement when you've decided that something will be an improvement, and you measure it again. And if it's not an improvement, then you perhaps throw that improvement away and say that was a bad idea. Or perhaps you say, well, if I did it a bit differently, then it would be an improvement, and you go around the loop again. So you keep going around that loop until you've finished. And I'm going to describe 3 or 4 iterations around that loop that we did on this particular process. The task we set that we decided to measure was using the compiler to compile itself. I have to confess that was a mistake. Well, it was a good idea in some ways because it made me a lot more familiar with the compiler. It's a mistake partly because it makes your brain hurt, because every time you change the compiler to speed itself up, you're changing the task of compiling it as well. So you're not compiling a fixed style sheet. You're compiling something that's constantly changing as you change it. And you can never quite disentangle in your brain the problem that the source document and the style sheet are the same. The other reason it was a bad task to choose is that its performance isn't actually important, because it's only a job we're going to do once, and once we've compiled it, you never need to do it again, except when it changes. It would have been better to choose a task that people actually execute frequently. So the theory was this is a good proxy for, if this performs well, then compiling anything will perform well. So in that sense, it was a good choice. But it would have probably been better to measure the cost of compiling DocBook, for example, rather than compiling this. But it was fun. And it led to the temptation sometimes to make improvements that would only improve this task and wouldn't improve anything else. And so that's the danger, that you choose a task and you optimize that task to death, and you do things that aren't going to benefit the real world. So you've got to be very careful of that temptation, which can result when you've chosen the wrong thing to measure. So what was the baseline? The baseline was that compiling the compiler using XJ took 240 milliseconds. Compiling it using itself on the Java platform took about 8 times that much, 2,040 milliseconds. Compiling it using the JavaScript engine on Chrome took 90 seconds. And I'm going to concentrate on this one because we've only really just started the process of making this perform on the JavaScript platform. And we decided it wasn't a performance tuning exercise, it was a rewriting chunks of the product exercise. And I wasn't going to be driven by the deadlines of this conference to get that done, rather than doing the right thing, which was taking out the guts, particularly of the XPath parser on JavaScript and rewriting that, which we discovered very quickly was essential to get away from that enormous performance difference. I have to say that I don't treat getting down from 90 seconds to 3 seconds as being impossible. In some ways, if you've got a big performance gap to bridge, it's much easier than if you've got a small one. If I get a new Saxon release out and someone tells me that something has regressed in performance by a factor of 5, I say, OK, we'll solve that. I can investigate that. I know what to do. If someone's got a 10% performance regression, that's tough. If one Saxon release is 10% slower at a particular task than the previous release, it is very hard to know where to start looking for that 10%. If it's a factor of 5, you know straight away where to start looking, and it's going to be obvious. It's going to be, you know, one big glaring bug that you fix it and you've solved the problem. But the 10% is much harder. So a big performance difference is in many ways much easier to tackle, much easier to identify than a small performance difference. So the task we've set ourselves is getting from that 2,040 down to that 720. Why 720? Well, I sort of decided if this compiler ran 3 times slower than the Java compiler, that would sort of be acceptable in the market. In fact, it might even be commercially sound if we had an open source compiler that was 3 times slower than the one that you had to pay for. That might be a reasonable sort of commercial model. So, you know, combination of usability and some business thinking that we need to get money coming in to pay for these developments. We don't do it just for the love of it. Seem to suggest that 720 milliseconds, which is 3 times the Java performance, was a reasonable target to aim for and one that looked achievable. So that's what we're aiming for. How do you measure these things? Our top-level measurement is to run transform from the command line. With a minus t gives you an output as to how long it took. Minus repeat does it more than once. You've got to use minus repeat to get repeatability of the measurement. If you've got a task that's only taking half a second, then it's going to be completely swamped the first time by the job of initializing the Java VM, working out the hotspot compilation, doing all that kind of thing. So the first run is going to take 10 times as long as the second run. And it's only after running the thing for about 20 seconds that you start to get some stabilization of the performance. So that's a good way of getting the top-level figure. Just to show you what that looks like, you end up getting output like this. At the end, it says average execution time over the last 26 runs. In fact, if you run it 50 times, it will average the last, I don't know why it's 26 rather than 25, but that's probably an out by one bug. But it takes the number of repeats and divides it by 2, and then it just runs it for the first half, and then it measures it for the second half. And that's giving, this is running a different task. It's not running this one. And it's also running it with a lot of instrumentation enabled. But at the end, it tells you how long it took. And that's our baseline figure for what's going on. And I have to say, I run it inside IntelliJ. That's not ideal. It's not ideal because IntelliJ is doing all sorts of background indexing, and you name it. It's distorting the performance according. If you've just modified the source code, then it's going to be busy re-indexing your modified source code. It's doing all sorts of background stuff that tends to lead you to inconsistent results. Ideally, you would run all these measurements on a clean machine that doesn't change and is the same every time. But that's not practical in real life. Next measure I use is this minus TP, and that's the first way of getting a breakdown of the performance. Where are the costs going? A standard feature of the product gives you an HTML output. That's the first level breakdown of costs. Let's look at what that looks like. Is that legible? So down here, you've got an identification of the components by module and line number. And it tries to identify a template by the match pattern or its name or the variable name or function name or whatever. It gives you a count as to how many times it executed. It gives you the gross figures for the total time spent in that function and the average time in each execution. And by gross, it means including the things that it called. And then it gives you net figures where net excludes the things that it called. So it sorts it based on the net total time. And so we've got a pretty dominant template here that's far exceeding the cost of anything else in terms of the time spent there. And that's always good news because it gives you one place to attack in your first, if there's one place that's clearly a good opportunity and that's low-hanging fruit for performance improvement, this will tell you. And as the module name tells you and as the template name tells you, that's the template that's invoking the XPath parser. So it's no real surprise that an XSLT compiler is spending an awful lot of its time parsing XPath. Java-level profiling. If you're writing your own XSLT code, you might think that going into a Java-level profile isn't going to give you much information. because unless you know the internals of the Java code inside Saxon or whatever processor you're using, what on earth do all the method names and so on mean to you? Actually, it can tell you quite a lot, because there's quite a good chance that the developers have used reasonably meaningful method names. Let's have a look at the Java profiler that we get here. This is with a commercial tool called JProfiler. And this is actually running a version of the software where I spent the last week or two rewriting the way Saxon does namespaces, in the hope that it would give a performance improvement. And at the moment, it's a performance disaster. And I need to find out why, and that's why I took this snapshot to find out why. And I don't think I can improve the font size on this, but you can get a feel that it's got a real hotspot in there. It's got one method that's taking a very high proportion of the total time. And in fact, if you look at the other methods that are taking a lot of the time, you find they are very closely associated with that. It's called complex content outputter.start content, and I think you can get a sort of guess as to what it might be doing. One thing, if you look down these method names, you'll see they're all concerned with generating result trees. In a different style sheet, you might find that it's all concerned with navigating the source tree. Again, you'll get a sort of feel from that for the method names. In another style sheet where I had a user with a performance problem, all the methods were concerned with doing decimal arithmetic. And the Saxon profile that says which templates are you spending your time in won't reveal that all the costs are doing decimal arithmetic, because that's spread across the piece. So this is a sort of orthogonal picture as to what's going on. Regardless which template you're executing a lot of, this is telling you you're spending all the time doing tree construction, which is a sort of something useful to know. Two interesting techniques, one that I've talked a lot about in the past, which I call subtractive measurement. Subtractive measurement means if you want to know how long you're spending doing X, stop doing it and see how much time you save. So if you suspect that serialization is taking a long time, then configure the system so it doesn't do serialization and see how much faster it goes. That's the best way of measuring the cost of serialization. If you think you're spending an awful lot of time validating the syntax of names, then take a correct program where the names are all valid, cut out the code that validates them, see how much faster it goes. That will tell you. Now, you can't always do subtractive measurement, and a new technique I invented for this exercise I call additive measurement. Because sometimes you can't stop doing X because it's essential. So another trick, do X twice. See how much longer it takes. If you want to know how long it's taking to verify that your Q names have correct prefixes, then just change your code so it does that twice, or does it 10 times, and see if it takes any longer. And that will give you a feel for how much time was spent in that one particular function. I found that a really handy trick in this exercise. Repeatability of measurement. I won't go into this into too much detail. One of the real hassles with Java applications is that the measurements come out different every time. It is very hard to get repeatable measurements. And it varies on all sorts of things. And did you realize that if your CPU is hot on your laptop, then the machine is going to run much slower than if it's cool? That's an example of the kind of factor that you have very little control over for getting good numbers. Don't worry about Volkswagen. Use the best numbers you can. Don't use the average, because all the extraneous factors are going to make things slower. The best numbers are the ones that are actually most consistent and most reliable. They're the ones that are most used to you as the person doing the development. Don't publish them or submit them to certification authorities, but they're the numbers you should use as a performance engineer. So what we do, phase one, was about getting rid of that hotspot on XPath parsing. We found most of that cost was about establishing the static context for XPath evaluation. We used two techniques to get rid of that cost. The first was eager evaluation, which is because parts of the static context are the same for every XPath expression in the whole style sheet. They use the same global variables, they use the same global functions. You compute that once. And so we made changes to only compute that part once and use it repeatably. The other technique is lazy evaluation. Lazy evaluation says don't compute it unless you need it. And for a lot of the rapidly changing parts of the dynamic context, like the namespaces, working out the namespace context for every XPath expression. Most XPath expressions don't care what the namespace context is. So don't waste time computing that unless the XPath expression needs it. Techniques like callback functions to get the information when needed can be very useful for that. That got us down from to this bar here, down to 1280 milliseconds. So quite a lot of good progress. The next phase was much more disappointing. Here, try to tackle lots of little things that gave a 50 millisecond saving. It's very hard to measure a 50 millisecond saving. We don't know which of these things were really helping and which weren't. Overall, doing, here's a list of 5, but we probably did 10 or 15 little things and only got another 100 milliseconds off. So that phase really was a frustrating one. There will be frustrations when you're doing that. There will be stages that are achieving nothing. So stood back. Last year at XMLPrague, I gave a talk about tree copying. How can we devise better methods of doing tree copying that don't involve the physical cost of copying a tree to another tree? There's masses of copying in this style sheet. In that respect, I was right. This application spends most of its time copying subtrees. Now, the technique I described at the conference last year was implemented in Saxon 9.9, and it should have helped. Firstly, I found it wasn't working as often as it should, so I tweaked it so that it actually was used more often. But then I measured that there were no performance benefits from it at all. Now, in the lab, it had given enormous performance benefits, so that was a great disappointment. I found the reason it was giving no performance benefits was all to do with namespaces. This style sheet uses about a dozen namespaces. I found that tree copying was quadratic in the number of namespaces because the semantic rules for copying namespaces across are very complicated. And I'd addressed the cost of copying the elements and attributes. That was coming down close to 0. The cost of copying the namespaces was still exactly where it was, and that was the dominant cost. So that's what I'm looking at now, but it was a great disappointment to find that all the work I'd done on tree copying made absolutely no impact at all. What I did instead was I looked at the XSLT code, and I said, let's do less copying. And we found various ways to avoid copying subtrees and eliminate the cost of that. And doing that avoidance of copying got us down to about 820 milliseconds. So we're now in good reach of the target. Phase 4, we looked quite hard at a couple of the serious algorithms we're using. And you've got to stand back and think radically about it's very easy to get bogged down in detail with performance. There were 2 important algorithms that were leading to a lot of cost. One was the cost of computing import precedence. That's described in the spec as a post-order traversal. So you read a subtree, and then you decide what the import precedence is, and then you basically have to attach an attribute to the tree that you've just read, which means you have to attach an attribute to a tree that you've just read, you have to copy the tree. So it would be much nicer to have an algorithm that computes that works on a pre-order basis, because then you can write the attribute at the time you're visiting that node anyway. And so I devised an algorithm for import precedence that works on a pre-order traversal, and that saved us a lot of copying, which was very successful. The other thing we were spending a lot of time was parsing our representation of types, sequence types, As I say, tree decorations have to be in string form. We were spending a lot of time parsing that and unparsing it. Devised a new representation, a very concise representation for sequence types that's very fast to parse, and also gave some benefits because a bit like the thing Adam was describing, you can work out whether one subtype is another by looking at whether one string is a substring of another. So it gives you fast analysis of the type hierarchy. That got us to 725. So we're now within an absolute whisker of the target, but perhaps it's not quite time to stop yet because we haven't quite made it, so we've got an excuse for carrying on a bit further. And then I thought, there's one trick in the book that we haven't used yet, and that's multithreading. So let's add one attribute to the style sheet. Let's say Saxon threads equals 8 in the right place, which is where we're doing XPath parsing. And that got us down to 550 milliseconds. So we actually overshot the target quite nicely. What about Node.js? Ask us next year. The Java side took longer than intended, but we'll tackle that next. So observations, it can be done. Debugging a style sheet like that is ruddy hard work. The biggest spin-off for you if you're a Saxon user is I've put a lot of improvements into the debugging capability and the diagnostics in the course of this. Because when you're eating your own dog food, you really think, why is that diagnostic so lousy? I could improve that. And the biggest spin-off is not a faster compiler for you. The biggest spin-off is better diagnostic capabilities in the product for you to debug your own complex style sheets. And if you're doing performance, you have to be prepared to stand back. You have to be prepared to tackle big things, to tackle algorithms, to tackle data structures, to refactor radically. Don't think you can do it by tweaking little things and minimizing the amount of change. You've got to be bold. So that's it. Thank you.
So thank you very much. So questions over there from Robin?
Robin.
Thanks very much, Michael. That really very interesting and fascinating how you improved the performance. Just like to go back to the beginning. You were talking about the Ceph file. I'm just wondering from the security point of view, is that reverse compilable? Could you produce some interesting or useful source code from that?
It's probably about as reverse compilable as Java bytecode, in that if someone makes the effort to do it, then it can probably be done. But it's more effort than most people would be prepared to go to. So yes, it's obfuscated rather than it's not encrypted, sort of encryption level security. But if you're interested in protecting intellectual property, then it's a lot better bet than shipping source code.
Okay. I don't see anyone else, but I have a question. Is there? Oh, sorry.
Very interesting to listen to this presentation, and a lot of aha-erlebnissen that come across. Performance is a very difficult thing to tackle. But at one point you mentioned it would be nice to have maps as decorations on trees, or as annotations, yep, perhaps. Since you write it in XSLT, can't you kind of fake decorate things using accumulators, which could use maps, or doesn't that work in this particular
one
scenario?
technique we've used is to use memo functions. So if you have a function to convert from a string representation of a type to a map representation of a type, then you use memo functions to do the two conversions. And so if you're doing the same conversion repeatedly, then you cut the cost of doing it. But
With memo functions, you mean XSL function, cache?
XSL
Yes.
function cache equals yes,
Yes.
or whatever. So that can help in that case. But you've still got the point that if you want to put structured data onto an XML tree, I think it could be a lot better. We could devise a mechanism to allow, in effect, a map-valued attribute as the typed value of that attribute and a string as the string value of it, or something like that.
Maybe we should extend the XDM to allow that. Thanks.
Okay, so we can set up this XMLPrague standardization body and work on XDM extension.
I have one last question, unless someone else? No. So what was the impact on the Java implementation of the compiler? Because you improved the XSLT compiler. So what was the symmetric improvement?
Very little. There was an impact on the XPath parser. Because both compilers are using the same XPath parser underneath. We found there were speed-ups in the XPath parser we could make. One of them was a very neat little trick. We discovered 50% of the XPath expressions in the style sheet are 5 or fewer tokens. They're all very short. And we found if you tokenize the XPath expression, you can then match the sequence of tokens against a dictionary of well-known sequences of tokens.
Okay.
And if you've got a $sign followed by a name, followed by a plus sign, followed by an integer, then you just look that up, and you know it's adding 1 to the value of a variable, and you don't need to parse it. You've seen expressions with that sequence of tokens zillions of times before. So just look it up in a database, and a database of 25 well-known token sequences saves you half your parsing cost.
Okay. Interesting.
Okay, I have additional question. So you mentioned that the slower performance of XSLT compiler, you are considering to having the slower open source version and then some commercial based on Java?
Possibly.
Yeah,
possibly.
so it could be that it will be possible to use open source Saxon to generate SF files?
Yeah, that's quite a possibility. That's something I would like to do.
Sounds interesting, thank you.
Because it's definitely an obstacle to the take-up of Saxon.js that there's no open source solution. So having a purely open source solution, I think, would create a user base which would increase our net revenue.
That sounds cool.
This isn't a conference for talking about business models, but
okay.
You can't separate business and engineering, I think.
We can do some incentives to developers. Okay. Okay, there is a question from Abel. And from, I don't know, but... So the first will be this question because Abel already has spoken question. You have to be fair.
Does this kind of work have any bearing on the viability of Saxon, compiled Saxon style sheets as a process for kind of serverless architecture, XML processing?
Generally we are attacking an increasing range of platforms all the time, and the big problem is that the amount of testing that you need to do rather than anything else. So, the varieties of platforms like headless and mobile and what have you is purely limited by the testing effort to ship things out.
Thinking specifically about stuff like AWS Lambda and other kind of functions as a service platforms where the real killer is the startup latency when you're being billed by the millisecond.
Yeah, I haven't looked at the performance impact of those platforms. The thing that we have most trouble with platforms like that is the commercial end of them, as to how on earth you price for people running in that sort of environment, which is something that no one seems to have a good answer to.
Okay, Abel?
I think I heard you saying in the beginning that this was meant to be open source or freely available?
No decisions have been made.
But hold on, that's not the question. The question would be the style sheet that you wrote. Did you use extensions, Saxon extensions, or was it purely?
Yes, there are one or two Saxon extensions. We've tried to minimize that. Obviously, calling the XPath parser involves a Saxon extension. For example, use when variables and static expressions. We evaluate using XSL evaluate. But we found that the restrictions for what you can, the functions that you can call in a static expression are slightly different from the functions that you can call in XSL evaluate.
I can imagine.
So we had to put a Saxon extension in to say allow XSL evaluate to do the things we need to do rather than the things the standard allows it to do.
You mean something like calling fn current or something?
That sort of thing,
which is not allowed in XSL evaluate.
Yeah.
Got it, thanks.
Okay, so thank you again, Mike. It was very interesting.
Thank you.
So this was last session for today, but we are not finished yet.